So in other words, which elements, little y here, get mapped to EH, right? So the question we're asking is, which elements y, little y, and these are elements of big G, your first group, your starting group, right? Your domain, if you like. And H is the group you're mapping to, your codomain, your target group, if you like. Right? So we want to know what are these y's? Which elements in G map to here? The y's, in other words. Now, by definition, we want to know the y's that map to the unit. So let this subset S here be all those elements, all the y's that map to here. Okay? Now we're talking about the unit. Now, what is the unit of H in this context? Well, it's n, right? So, what is the unit of H? Right? This the group we map to. This quotient group. You call this H, right? G to H. Well, it's n. The unit of H, or this, is n, right? So you can rewrite this E of H, the unit of H, as n. Okay. So f of y equals n. Right. So shelve that for a while. Keep it on the back burner for a little while. So f of y is n because E of H is n, which we got from here. Okay. All right. So forget about that for a little while. But and we're still analysing a bit. We'll get a few more facts and put them together, and then we'll use this theorem and get quite an interesting result. All right. Okay. So we've got this result. Now, what is f of y? Well, from here, if we just put y here, f of y is just yn. Okay, by definition, that's how we defined this function, this homomorphic function f. Right. So f of y is just yn. Okay, but we also have from here that f of y is n. Okay. So we've got f of y is yn and f of y is n. So here's your f of y is n, and here's your f of y is yn. Right? Both are true. All right. Well, if f of y is yn and f of y is n, then obviously yn equals n. All right. If a equals b and c equals b, then a equals c. Right? Just simple logic, right? So that means that yn and n here are the same. Okay, so n equals yn. All right. So we've shown that to be. So n equals yn. Now we can use this bit of 46 theorem part 1, right? So if yn equals n, or n equals yn, same thing. Which we've got, right? Now from 46.1, if n equals yn, that implies that the y belongs to n, right? Y belongs to n. So from this, using this, we can deduce that y belongs to n. If that's true, but it is true, here it is. So if that's true, then this is true. Therefore, y belongs to n. Right? So the answer to our question was, which y's map to the unit of h, or the unit of this? And the answer is, well, the y's that belong to n. Okay? So our subset here of group G is in fact n. And what is n? N's the normal subgroup. Okay? So the normal subgroup N, its elements map to the unit. That's what we've shown. That's what we've proved. Right? So the answer to this question, which elements of G map to the unit of your H, the answer is N, the normal subgroup. Right? Its elements, they map to here. Right. So yet another example of asking that question, which elements of G map to the unit of H. This concept has been reinforcing it, Barnard and co-author. Poor old co-author who never gets a mention. That's the disadvantage of being second author. Okay, alright, so now the trumpet roll, ta-da! Finally we can come to the introduction of a critical concept in group theory, finite group theory, an important one, and it will play a very important role increasingly in the future. It's the concept of the kernel, K-E-R-N-E-L, right? German word, I think it means kernel, like the heart or the center or the core, right? So I guess some German mathematician invented it, right? So by definition, what is the kernel? Well, it's the subset whose elements, all of them, map to the unit of your H. This is in the context of a homomorphic mapping, right, from G to H. So you're mapping from G, group G to a group H, right? So this subset, call it S, subset of G, its elements map to the unit of H, right? So S is a subset of G. Expressed in a slightly different way, the kernel is the subset of all elements of G that get mapped to the unit of H. Right? You just collect them all together and call it a subset S, so that that subset gets mapped. Every element in it, S, call it K, like kernel. That subset gets mapped to the unit here, H, right? That's the definition of the kernel. Okay. And so in the context, you're mapping F as your function. It's a homomorphic function. It's mapping these two groups, group G into group H, and for every member of your subset, S is a subset of G. So for every member of that subset, the homomorphic function maps that member, X, into the unit of the second group, H, the unit of H. Okay? Now that subset is so important, it gets its own label, special label, and it's called KER, Ker, which is just short for kernel, obviously. Right? So it's the kernel of F. So if you see this expression, Ker F, it just means it's the subset of G that when you map it using function F, when you map it into group H, that subset, all its elements will map into the unit of H, right? E of H, right? The unit of H, not G, the unit of H. Alright. Now, we've seen several examples where these kernels, these subsets that map to the unit here, are actually subgroups, not just subsets, they're subgroups. Right? So, in fact, here we will prove that a kernel is a subgroup. In fact, we'll go further. We'll actually show it's not only a subgroup, it's a normal subgroup, right? which is interesting. So a kernel is a subgroup and a normal subgroup. All right. Well, let's prove. Let's do the proof. So we'll first prove that it's a subgroup, right? And in a second step, prove that it's a normal subgroup. So we'll take two bites at the cherry, right? Okay, how do you prove anything is a subgroup? Group. Well, you have to prove the three properties, right? We've done this quite a few times. So to prove that a subset is a subgroup, just a minute, I'm going to increase the, or lower the temperature of the air conditioning. It's getting a bit hot. Okay. Right. The brain, I think, absorbs something like 40% of your calories.